Hey everyone, please ignore the discussion of sunscreen in Twitch chat below. Today we have a problem from the Harvard MIT Invitational competition from 2015, which goes, suppose that omega equals e to the 2 pi I5 over 5 is a primitive fifth root of unity. And you want to prove that there aren't integers a, b, c, d, k with k greater than 1, such that this power all to the k is equal to 1 plus w. Omega, sorry, 1 plus omega. So the first thing I want to say is that 1 plus omega squared plus omega third plus omega to the fourth is equal to 0. And my point of saying this is that really this is saying, and that means that this thing in here, we're living inside z adjoin omega. And this is a bit hard to do properly without algebraic number theory, which is a little characteristic of like Harvard MIT Invitational competitions. They try to push the border of what's considered acceptable knowledge. Apparently today, algebraic number theory is considered acceptable knowledge. So what happens is you can phrase the problem here as saying, consider the ring, we'll call it just R, which is z adjoin omega. Show that 1 plus omega is not a perfect power. And I believe it is a known fact. In fact, I'm actually going to call this O sub k for reasons I'm going to elaborate on in just a moment. I don't know. Because what happens is this is living inside the field k equals q adjoin omega. So the number field, this number field has dimension 4 over q. So I'm trying to think of what to say in a way that doesn't be too annoying. Yeah, I'm sorry. I'm pretty sure the way this problem is written, I'm not going to be able to get away with not doing this shit. But so roughly, this is a structure that has. You can think of it as a generalization of the rational numbers, and this is its corresponding integers. So So basically the objects that the audience here is familiar with are like z and q. Z is a set of integers, q is a set of rational numbers. So the integers you can add, multiply, add, subtract, and multiply, but you can't divide in the sense that the quotient of two integers might not be an integer. However, z lives inside q, meaning that in the rational numbers you can divide in the sense that the quotient of two rational numbers is a rational number. So we say that z is a field and z is a ring and q is a field, and in fact z is the ring of integers of q. It would take me a lot of effort to define it properly, so I will just tell you there is an analogy here where k is the field, and this thing, the linear combinations of omega, like in the problem, are the ring of integers of k. Sorry. Now, why do I bring this up? When for higher dimensional things like this, there is a notion of a norm. There is going to be a map, and there is a proof that overline. Yeah, I agree. Well, I think the hard part is not that k is the. I think it's easy to show k is a field of fractions of OK, but I think it's more non-trivial to show that OK is the ring of integers of k. Anyways, there's a norm map. Okay, there's a norm map. So this norm map will take q adjoin. It'll take OK into z. So for every element of the ring of integers of k, it's going to assign a number. And if you haven't seen this before, the example to keep in mind is there is a map. In the case for z adjoin I to z, it's the absolute value squared. So this is a two-dimensional example, and this map has the property that it is multiplicative. So first what I'm going to do is I'm going to compute n of 1 plus omega. And it's a theorem that this is equal to the product of the product of the Galois conjugates. So it's equal to 1 squared, 1 plus omega cubed, 1 plus omega to the 4. And where omega is our fifth root of unity. Is it really not possible to do this by setting w equals cosine 72 plus I sine 72? I don't know what you mean by that. Like, you gave me a different expression for omega, and I don't know what you want to... Like, I don't see how that expression makes the problem easier, I guess. So I don't know what approach you are trying to lead to. By comparing real and complex parts, I am skeptical. Yeah, that feels like it's going to be heavy. Okay, anyways, I'm gonna do the expansion now. So, this is the part that I think people here should be able to do. Because... multiplicative. This is a like elementary calculation. So the way you do it is that it's minus 1 minus omega, minus 1 minus omega squared, minus 1 minus omega cubed, minus 1 minus omega to the 4th. So this is the result when I plug minus 1 into the 5th cyclotomic polynomial. And the 5th cyclotomic polynomial is x to the 4th plus x cubed plus x squared plus x plus 1. So this is equal to 1. Oh no, it's equal to 1. I was hoping it would be equal to something that wasn't... No, really? So this is a unit. Okay. I thought this would be equal to 5 and I'd be done. But... Wait, is it actually 1? Can you guys make sure it's... Okay, never mind. I thought this was going to be equal to like a prime and I would be done. Okay, well, so much for that. Alright, now what? So, this is telling me that 1 plus omega is a unit. And actually it's equal to these things. That's not good if it's a unit. I can just consider other units, right? I could classify... Oh, jeez. Dude, I don't know this stuff either, but there is a theorem for this. So there are there are exactly 4 embeddings of Q adjoin omega into C according to omega maps to omega to the K for K equals 1, 2, 3, 4. And so what I can do here so Dirichlet's unit theorem implies that, well, so K has signature 0, 2. So Dirichlet's unit theorem implies that unit group of OK star has rank 1. So if the problem is going to be true, actually OK star should be exactly generated by 1 plus omega. So if the problem statement is going to be true, what this problem is trying to tell me is that every unit of Q adjoint omega is a power of 1 plus omega. Does HMIC guarantee an elementary solution? Nah. Okay, I think that I just baited myself really hard though. I feel like I pulled out all the fancy things and I know what the problem is trying to do now, and I'm not gonna get it this way. There must be something happening. Is there some finite field you can embed this into? And the problem is that it's because it's a unit, what that means is that, well, Okay, so what has happened so far? We concluded that 1 plus omega actually has a reciprocal, namely 1 plus omega squared times 1 plus omega cubed times 1 plus omega to the 4th. And I did some fancy black magic and concluded. So this is the set of all units. I should use times, not stars, sorry. To be consistent with my past self. Man, I was really hoping it would have norm 5 or something. How can we be sure that 1 plus omega is a primitive unit? That's what the problem implies. If 1 plus omega is... So 1 plus omega is a unit, and the problem is saying it's a primitive unit. That's what... yeah. Oh, no, sorry. I forgot the torsion part. Thank you, Tayonyo, for the raid. Oh man. Alright, so for people new to the stream, hi there. I'm Evan. I am a Math Olympiad coach. Welcome to my stream. I stream every Friday at night starting at 8 p.m. And this usually consists of me doing math with my viewers for a while until I am too tired to do any more math, at which point we start playing random video games and so on. Thanks for coming by. Yeah, and right now we're getting algebraic number theory happened. On answering questions from chat. Ah, okay. What is your major or research topic? So I'm actually pre-quals. I haven't passed my qualifying exams yet, but my intended area of research is modular forms. Thank you, Crypto Mathian, for the follow. Okay. Yeah, so we think 1 plus omega is generating the full. Did you already consider an advisor? Yeah, Wei Zhang. Is magnitude of thing being raised to k? Thank you, MHZ, for the follow. Thank you, Portrays, for the follow. Truce. Yeah, I don't see it. So the idea that's being suggested is we could, let's see, yeah, because omega plus 1 over omega happens to be the golden ratio, we could try to take, rather than the norm from OK to Z, you take the norm from OK to Z adjoining 1 plus root 5 over 2. So only one level down. So degree 4, it's one level in between. Maybe units of it are good. Okay, let's see. So, okay, let me. I think the units of Z adjoint golden ratio are powers of golden ratio. I would believe that. Okay, so. So we're going to take a Q adjoin omega to the one below, Q adjoin root 5, was it? So this will map 1 plus omega to 1 plus. How does this map work? I guess this map might actually so the map you're talking about might actually just be like a straight absolute value. Actually, this map might just be like Z maps. I think this is Z maps to Z squared, like standard complex absolute value, and this map will take 1 plus omega to 1 plus 1 over omega, which is still a presumably still a unit, right? What is this equal to? It's like 2 plus omega plus 1 over omega. So this is equal. Oh, actually, this might not be. Where are you writing? I'm writing in a LaTeX document, yeah. So if you look at what the desktop looks like, this is the thing I'm working with. One of the monitors I'm working with. Does MIT PhD program take qual after second years? So at MIT, you take your qualifying exams before the end of your fourth semester, so second year. I'm taking it a little bit. Sorry. Most people take it a little earlier than that. A lot of people take it by the end of the third semester. But I've been away from school since like around last March, so I am behind everyone else as a result. Okay, so this is where so unfortunately I don't actually know what cosine 72 degrees is. But this sounds like it might matter because it's not going to equal 1 anymore, right? Because of COVID? Among other things, yeah. Square root 5 minus 1 over 4? Thanks. Times. Okay, thank you, Twitch chat. That is good to know. So, square root 5 minus 1 over 2. So this is like root 5 plus 3 over 2. So I can't take the norm again, because if I take the norm again, I'm going to get 1, which I already knew. But this is good, because this number is not 1. And in fact, this is 1 plus. This is phi squared, where phi is the golden ratio. Okay, let me move this stuff here. Okay, so I actually like this a lot. Yeah, the pandemic. Yeah. Yeah, I've just kind of taken a while away from school. Phi squared. So if there was actually a number such that I have no idea what I'm seeing, but I like it. It's okay, I don't know what I'm doing either, to be honest. So cool. So if there was a number z such that like z to the k was equal to 1 plus omega, then taking the absolute value squared of both sides would imply z to the 2k is equal to phi of phi squared, or z to the k is equal to, well, we'll just do it that way. Z squared to the k. Okay, so I am feeling that this should reduce the possibilities for k, because I guess it becomes a question of like, is 1 plus phi a power or something? Well, okay, phi is still a unit because phi times phi minus 1 is equal to 1. Yeah, 1 plus phi is a power of phi. On the other hand, what is the unit group of... So z adjoint phi is the ring of integers of q adjoint root 5. But I think this is a Pell thing. Like, because it's so concrete, it's like this root 5 thing, I think it's actually given explicitly by like so and so minimal unit. Is that right? Yeah, so I believe z adjoint phi, this unit group should be generated by... Actually, I think it's just generated by phi, right? How much time do you have for this problem on HMIC? HMIC is a 4-hour 5-problem exam, I think. So you'd have like a couple hours at most. Yeah, I think phi should be the fundamental unit of... I think phi should be the fundamental unit. So if that's the case, absolute value c squared all to the k is equal to phi squared. Yeah, I think phi should definitely be the fundamental unit here. I think my question is, does that should imply, so this absolute value z squared is also an element of z adjoint phi, and therefore, like either like we have to have, I think. Thank you, Raxo Sabi, for the follow. Yeah, I think the only way this happens is if the only case we're worried about is if k equals 2 and like z squared is exactly equal to phi. I almost want to say that shouldn't happen, but I'm not sure. So like, can absolute value z squared be equal to phi? And maybe this is the point. I mean, now that I have it down to this, do I want to just... if I'm going to grind this out manually, I should have just done that to start with. How old are the kids in Olympiad competitions? They're all high school. But this is a bit of an edge case. Most of the problems that I get asked on the stream do not look like this. Yeah. You want me to grind z squared? I don't know if I can do it. I'm old and delusional. But yeah, the only case I'm worried about is k equals 2, absolute value z squared equals 2. Is this really phi squared? Can this please just be phi? I want to be done. It's not phi though, is it? 1 plus omega, yeah. No, hang on. Oh yeah, yeah, because it's squared. So 2 plus omega plus 1 over omega. 2 plus 2 cos 72. All right, people are cheering me on. Okay, we'll try to expand. I'm not sure it's gonna work, but we'll give it a shot. All right. Okay, so I'm actually going to... Oh my god. Meaning of Pell theory. Basically, Pell's equation is talking about what are the units of real quadratic fields. And... Okay. Okay, so when I expand... Oh, never mind. Someone already expanded. Alright, thanks. We'll take that. I hope you're right about that expression. Phi minus 1. Okay, so when you expand, apparently you get this. Which I'll just take on faith for now. Someone please double check this calculation. Do I believe this? Why write phi minus 1? Well, because it's z adjoint phi, and it's two-dimensional, so... Not 1 over phi? No, so z adjoint phi has, is 1 and phi. That's the generating basis. So that means every element of z adjoint phi is uniquely expressible as x plus y phi. And so that's why I want to write phi minus 1 instead of 1 over phi, because I want to use that basis, because I'm trying to brute force my way into finishing the thing. So, you guys are sure that this is the right expansion? Okay, I'll take that at face value then. Evan, please verify. Oh, alright, fine. Okay, so A plus B over omega. Yeah, wait, this AC coefficient is not... I'm already having a discrepancy, sorry. That being said, I don't think we should use ABCD as derivative anyways. Thank you, Francor1010 for the follow. I think what I want to do is, I want to write it this way. So this is only different by a factor of omega, but it has the advantage that it's more symmetrical. And then I can do minus 1, minus 2. This is minus 3. This is minus 4. And so... Okay, so the a squared plus b squared plus c squared plus d squared is definitely there. And then we get some different things. So the coefficient for omega to the minus 1 is given by ab plus bc plus... The ones that are off by 1 are a, b, b, c, c, d. Yeah, this will get a phi. And the ones that are off by 2 are AC plus BD minus AD. I think. Let me double check this. Yeah, I think this is better because this is more symmetrical. Is that correct? No, I think it's actually plus. You get dA omega cubed and then dA omega squared. Is that okay? So I think this is what it should be. If I use these variables, this is better because it's symmetric. And then I can write a squared plus b squared omega to the second omega to the minus 2. This is phi. And then this is a plus 1. Why can we do this? Because omega, omega squared, omega to cubed, omega to the fourth is another integer basis for z adjoint omega. So I'm just changing the variable name slightly. Okay, everything looked believable up to here? So what we've done is, rather than take the full norm from the top to the Q, we took the norm from Q adjoin omega to Q adjoin root 5, which happens to just be taking the absolute value squared. The absolute values all live inside Q adjoin root 5. The ring of integers is generated by the golden ratio. And we get this equation. This is the key equation. So the only case we have to rule out is where k equals 2 and some z has... Yeah, then some z has square equal to plus minus v. So at this point, I'm not terribly surprised this is happening because I'm imagining... Yeah, we are stepping down 2 dimensions. Thanks to Cool Burrito for the follow. And what I'm imagining is going to happen is that we kind of do this case by hand. So we use the absolute value so that we don't have to expand to the fourth, we only expand to the second power, and then we try to do the second case manually. And so the question is, if I did the expansion correctly, I want to show there's no integers a, b, c, d, such that this is equal to 0 plus minus v. So in other words, I want to show this system of equations has no solutions. Plus minus 1. So it comes down to this system, which I don't know if I'm going to be able to... Basically, if I take the absolute value again, like the root 5, I'm going to end up with... I'm going to end up with a unit, which is not what I want. Isn't first equation always positive, the left-hand side, by sums of squares? Is it? So you're telling me the left-hand side is equal to... Okay, let's try that. A plus c squared over 2 plus b plus d squared over 2 plus Wait, actually? Is that it? Do I not even need the second equation? That seems too good to be true. Wait, does this work? I don't believe this. Wait. Okay, so let me summarize the solution so I have it correct in my head. We replaced the variables with 1, 2, 3, 4, so it's more symmetric. It's easier to think about that way. We said if this is equal, if this happened, we took the absolute values. On the right hand side, we got v squared. And on the left hand side, we got this expression. All to the kth power. And k is not equal to 2, and k can't be a higher power because of Pell theory. And then to solve this equation, we just do that. Well, that was not how I expected it to end. The what? Well, okay. Let's see what. So I know the guy who set this HMIC very well. The guy's name is Victor Wong. Oh yeah, that's actually the solution. So this forces k equals 2, and then he gets the system equation. Alright, we did it! Alright. I can't believe that's actually the solution. Alright, well thanks everyone for tuning in. It turns out we didn't need to do that much fancy stuff. The only bit that was fancy that we actually needed was that the golden ratio was strong. Is there a clean way to phrase the connection between x to the 5th minus 1, that polynomial, and x squared minus x minus 1? I don't feel... I think what's happening, I mean, so the official PDF phrases it pretty well, which is that there is a tower of extensions. Like Q adjoint root 5 lives inside here, and Q is the base field. And it so happens that I think you think of x squared minus x minus 1 as the well, okay. Sorry, let me scroll a little so my head's not blocking. Why does this tower exist? So Q adjoint zeta is a degree 4 extension whose Galois group is Z mod 4. And the fundamental theorem of Galois theory tells you that because Z mod 4 has a subgroup Z mod 2, there must be some intermediate field, i.e. the intermediate subfields are in bijection with subgroups of the Galois group. So Z adjoint 4 has a simple subgroup structure as Z mod 2 and then to Z, so that will correspond to some tower of fields here. Their z-squared expression is slightly different. I think we used different variables than they did. Yeah, I changed the variables slightly because I wanted it to be more symmetric, so I'm not surprised the expression in the official solution packet might look a little off compared. Okay, so that concludes this problem. Hope you enjoyed. If you want to learn more about this algebraic number theory stuff, read the napkin. I wrote it up I wrote it up for you. And yeah. Man. This is not usually what happens with the problems. The next problem I promise will probably not be quite this fancy. Did you include this problem in the napkin? No. Although I probably will now. In general, I only solve problems on stream that I haven't seen before because the point of this stream is I want to show people like what my thought process is when I go through problems that I haven't seen before. Can you see the problem statement? Yeah, you want to show that 1 plus omega is not a perfect power in z adjoint omega. This is definitely an integer polynomials problem as far as where I'm putting this for my students. Napkin does not have much analytic number theory, sorry. But there's a really great introduction by Hildebrand that I really like. I'll link it in the chat. Yeah, so that introduction I linked is the analytic number theory introduction that I like the most. Yep. Okay, let's go back to high school.